Hi, I am Prasanna, a PhD student at Georgia Institute of Technology. Today, I will be discussing a fully integrated AI-driven framework for rapid endurance prediction in non-volatile ferroelectric DRAM capacitors. While the results presented during this talk today will focus predominantly on ferroelectric capacitors, the key takeaway of my talk is in fact the endurance prediction platform that can be adapted for reliability prediction across any device or technology. Let me start by framing this in the context of memory for AI. If you look at a modern NVIDIA GPU, the dominant feature isn't the compute cores, it's the memory stacked right beside them. That's the high bandwidth memory or HBM. At its foundation, HBM is built on DRAM, and for AI workloads, DRAM scaling and reliability are every bit as important as raw compute throughput. From a device perspective, what this means is that the bottleneck is no longer just performance, it's how reliably and how long these memory cells can operate. That is where characterization and modeling become critical. Endurance is one of the most fundamental metrics we deal with in DRAM technology. State-of-the-art DRAM cells are expected to survive more than 10 to the 15 write cycles. But here is the challenge. Endurance characterization simply doesn't scale. To cycle a single ferroelectric capacitor to 10 to the 12 cycles already takes about 4.5 days. That's just for one device. Now compare that to a full chip with an order of 10 billion cells. Exhaustive testing becomes impossible. This is the critical pain point. Endurance matters the most, but our ability to measure it directly is fundamentally limited, which is why accelerated characterization and predictive modeling approaches are becoming essential. So, one way to think about the endurance problem is this. If breakdown is ultimately driven by defect physics, and if we can measure the defect landscape early on, then maybe we don't need to cycle the device for trillions of operations or billions of operations. So here is the idea. We can experimentally extract an initial defect profile, parameters like trap density, trap energy distribution, relaxation energies. That profile serves as a kind of a fingerprint for the device. Now, imagine feeding that fingerprint into an AI model that has been trained to learn the mappings between these defect features, time t0 defect features, and the end of life or the endurance statistics. The Weibull slope, beta, and maybe the characteristic lifetime, etc. In principle, this would let us bypass long-term cycling entirely and instead infer endurance directly from the starting defect state. That's the vision. An endurance predictor that connects measurable physics parameters, defect parameters, to reliability outcomes. That would indeed be great, but of course there's a catch. To train such an AI model, you need large amounts of high quality training data, and in our case, experimental endurance data is extremely scarce. Each full characterization takes days, and scaling that to thousands of devices is simply not feasible. That means the very data we want to train on is exactly the data that we cannot afford to generate in large volumes. So while the concept of an AI endurance predictor is attractive, it immediately runs into this practical roadblock, the lack of training data. That's where we need to rethink how datasets for reliability modeling or reliability prediction frameworks are generated. So how do we get around this data bottleneck? If experimental datasets are too slow to generate, we have to look at alternative ways of producing the data. That's where simulations and AI come in. On the left, experiments give us only a handful number of data points per day. Contrary physics-based simulations like kinetic Monte Carlo based approaches can do much better. We can generate hundreds of defect profile trajectories per day. But even that falls short once we start thinking about wafer-scale variability. The real acceleration happens when we bring in AI surrogates, especially physics-informed AI surrogates. Once trained, we can generate tens of thousands of datasets per day, effectively bridging the gap between what's physically measurable and what we need to model at scale. So the strategy is clear. We combine experiments, simulations, and AI in a pipeline to unlock dataset generation at the scale endurance prediction demands. At the core at the core of the physics layer, we have kinetic Monte Carlo simulations. We use Ginestra, a defect-based modeling platform from Applied Materials. These simulations start from experimentally measured defect profiles and then evolve them forward in time. The kinetic Monte Carlo framework allows us to capture the stochastic nature of defect generation and transport, things like trap-assisted tunneling, bond breakage, and self-heating effects. In practice, this means we can predict how traps accumulate over billions of cycles and when the device will eventually break down. The good news is that these simulations produce very high fidelity data and they match experiments closely. The challenge is that they are still computationally intensive. Scaling them to wafers worth of devices would take far too long. That's exactly the gap we are trying to close with physics-informed AI surrogates. Now, let's look at our specific example, ferroelectric capacitors. We start with experimentally calibrated defect profiles of ferroelectric capacitors and perform kinetic Monte Carlo simulations using Ginestra. As an example, the evolution of defects in a 7 nanometer HZO capacitor with bipolar cycling at 2 volts and 25 degrees Celsius is shown here. Now, here is one example. So initially we have no defects, then after say a million cycles, we see defects being generated here, represented by the dots here, and then after a large number of cycles, we see a hard breakdown path being generated. The defect density or the evolution of defect density through these devices and through the cycles is shown here. First, it is shown for a single device. We see the exponential increase in defect density here, and the defect breaks down. This is for a single device. And then for 100 devices, we have shown the same, and we also show the log increase in defect density over cycles here, and once the defects start increasing, it looks fairly linear in this region. So what is important here are the statistics, and generally in the reliability community, statistics of breakdown is represented using a Weibull distribution. So, and we see here the Weibull represented. The circles, the white circles that we see here are experimental data, and the red dots that we see here are kinetic Monte Carlo simulations. And we see a fairly decent agreement of KMC and experiment here. This is what we mean by high fidelity data generation using kinetic Monte Carlo simulations in Ginestra. While KMC simulations produce high fidelity data, they are slow. So the solution is to replace these slow KMC simulations with an AI surrogate. We use NVIDIA's Physics NeMo framework, which is designed exactly for this kind of problem. It lets us train machine learning models while embedding physical constraints directly into the training. So we have the Physics NeMo model here. Physics NeMo comes with its own built-in model libraries. We can embed physics constraint into them, and these models are trained using the high fidelity physics-based simulation data that we generate using Ginestra here in this case. So this provides a AI surrogate that can go from the initial process parameters or the initial setup all over the way to the output. What this means is that instead of running a full KMC trajectory, we can feed in the initial defect profile, and the surrogate will predict the entire defect evolution over cycles in a fraction of the time. The key advantage here is speed. Once trained, this AI surrogate reproduces physics with extreme high accuracy, but gives us more than 3 orders of magnitude acceleration. That turns wafer-scale endurance modeling from something impractical into something entirely feasible. Going back to our specific example of ferroelectric capacitors, an AI surrogate based on a transformer architecture is used to model the evolution of defect density. The model is trained using the synthetic data generated using Ginestra's KMC simulations. The AI surrogate is the profile, the defect density evolution predicted using the AI surrogate is shown here in red, and the KMC simulations are shown here in black dots for 3 different cases, and they can be seen to be in very good agreement. That is also further confirmed by the predicted cycles to breakdown. We are able to predict the cycles to breakdown fairly accurately. So we see here we are predominantly between 90 to 95% accuracy with the R square of over 0.99. So in order to show some physics with it, we varied the polarizability. Higher polarizability means faster breakdown. And we can see the same trend here. So we represent the Weibull here because we want to study statistics. And we see that as the polarizability is increased, the AA surrogate, as expected, shows that the cycles to breakdown, the Weibull curves versus cycles to breakdown curves move towards the left, indicating faster breakdown. Now that we can generate defect evolution quickly with the AA surrogate, the next step is to connect that information to endurance statistics. Remember, what ultimately matters for reliability isn't the exact trap density versus cycle curve. What matters is when the defect fails and how that failure is distributed across a wafer or a die. So what we do is take the synthetic trajectories from the surrogate, extract the cycles to breakdown, and fit them with a Weibull statistics. That gives us a slope beta and the characteristic life eta. In other words, the surrogate gives us the raw physics data, and we use that to build up the statistical distributions that actually define endurance. To actually implement wafer-scale predictor, we use NVIDIA's NeMo framework. The idea here is straightforward. The AA surrogate gives us a large volume of synthetic endurance data, and the NeMo provides the scalable infrastructure to train and deploy the final endurance prediction model. We feed in the initial setup and process parameters along with synthetic datasets generated by the AA surrogate, and NeMo handles the training across its model library and outputs the Weibull statistics or the endurance statistics or the reliability statistics. So once we have enough synthetic endurance data from the AA surrogate, we can take the final step, training a dedicated predictor for Weibull statistics themselves. Here, instead of going through the whole defect evolution, we use a neural network that directly maps the initial defect profile to the Weibull parameters, eta and beta. So we have a statistics of the initial defect profile, variation in all the different process parameters, and then map it directly, defect parameters, and directly map it over to the Weibull parameters. Okay, let's think of it this way. If the surrogate is the heavy engine that generates lots of synthetic data, this model is the lightweight front end. Once it's trained, it can take the initial trap fingerprint, statistics of the initial trap fingerprint, and instantly tell you the expected endurance distribution across a die or a wafer. That means in practice, we can do a one-shot wafer level endurance prediction without ever running a long stress test or a heavy simulation. So let's go back to our example of ferroelectric capacitors here. So we use a multi-layer perceptron based model here to go from the initial statistics of the defect profile all the way over to the Weibull distribution. So we show a few examples here for few simulated initial statistics, and we show 3 things here. We show the statistics from kinetic Monte Carlo simulations, from VLPred, what we call as our final endurance predictor, and also from the AA surrogate. The AA surrogate we show in red, and the final endurance predictor we show in blue, and KMC we show in black dots. And we see fairly decent agreement between all these 3 for these shown 4 different cases. We also show the accuracy of eta, which is the characteristic lifetime or the mean cycles to breakdown here. And we also show beta, which is the slope of the distribution, slope of the Weibull distribution. We see that we are able to predict the mean cycles to breakdown with a fairly high accuracy. Beta, we are very good at predicting beta, especially for lower betas, but we are still yet to figure out what is going on with higher betas. It is also about scaling the datasets. Now that it is established that we have built VLPred, which is our AI-based endurance predictor. It enables us a rapid prediction or a one-shot prediction of endurance statistics from the initial defect profile statistics at a die or a wafer level. So here, as a small short demonstration of the capabilities of VLPred, our one-shot endurance predictor, we show a wafer level endurance map predicted from a simulated initial defect profile. So we have color coded the defect profiles for defect profile statistics for it to be easily visible. We see that here on the left, and then we see the predicted Weibull distribution over on the right. This is just a quick demonstration of the capabilities of the VLPred platform that we have built. So what really matter is the wafer level characterization numbers. What are the numbers? How fast does it go? So a full endurance test out to 10 to the 12 cycles takes about 4.5 days just for one device. Even with physics-based KMC simulations, we are looking at minutes to generate each trajectory. With the surrogate in place, the same trajectory can be produced in seconds. And once the endurance predictor is trained, we can do one-shot endurance prediction of the Weibull distribution across an entire wafer or a die in a matter of a minute or lesser. That's more than 10 orders of magnitude reduction in characterization time. So once a model is fully calibrated, we can do all these characterization, all these AI augmented characterization significantly faster, going from something that was effectively impossible at a wafer scale to something that's now a routine. So AI augmented endurance characterization now could be a routine. To wrap up, what I have shown you is not just a faster way to do endurance testing, but a different way of thinking about reliability altogether. By combining experiments, physics-based KMC simulations, and physics-informed AI surrogates, we have built a pipeline that lets us predict endurance distributions at a wafer scale in minutes, something that was unthinkable with traditional methods. But the vision here is broader than ferroelectrics or DRAM for that matter. Any dielectric reliability problem that involves defect generation or statistical variation can benefit from this approach. Not just endurance, any reliability metric can benefit. What we are really doing is turning reliability into a data problem and then using AI to scale it. As memory technologies continue to evolve and as AI workloads place even higher reliability demands on memory systems, we believe this kind of physics-informed AI frameworks will become a central tool for accelerating device characterization and enabling the next generation of memory devices. Thank you.